Right, welcome to the fourth video for chapter 4. We're moving into section 4.3, which is the central limit theorem. Okay, also referred to as TLT for brevity. So the setup for the central limit theorem is we'll often be given a random sample of data. So let's say x1 up through xn. And the sample mean, so the sum of the data divided by n, is frequently used as a test statistic to answer some kind of null versus alternate hypothesis question. And it turns out the central limit theorem gives us a method of approximating a lot about the distribution, the sample distribution of x bar, namely its mean and its standard error or standard deviation. Okay? So the idea behind the central limit theorem is that for large enough values of n, x bar is approximately normally distributed. And that's pretty profound. And that's independent of what distribution x1, x2 up through xn originally came from. X bar will behave in a somewhat normal fashion for large n. All right, so statement of the central limit theorem. We've got x1 up through xn. They're independent and identically distributed random variables, each sharing the mean mu and the variance sigma squared. And we need that variance to be finite. Okay? Then the outcome is x bar is approximately normally distributed and the mean is still mu and the variance is sigma squared over n. And as I'll sort of talk about in the next panel, these two values should not have been a surprise to us. Okay? Being normally distributed, that's a bit of a surprise. Okay. All right. And as n gets bigger and bigger, this approximation gets better and better. X bar behaves more and more normally with mean mu and variance sigma squared over n. Okay. Or in other words, if I were to standardize x bar by subtracting its mean and dividing by its standard deviation, it starts to look like the standard normal variable. Okay. Which is kind of what I say up here. What we'll usually do with x bar to do any computations with it is we'll standardize it. So we'll subtract its mean, divide by its standard deviation, and now this will be approximately normal and approximately standard normal, n0, 1. All right, so hopefully you paused, copied, and then listen to me chunner. All right, so again, I want you to pause, copy this down, and then I'll chunner along. Okay, so the mean and the variance in the central limit theorem should not have been a surprise. We've done, in the last few videos, we've done several times where we've calculated the expected value of x bar, like drag the 1 over n out, split the expected value up, expected value of x1, expected value of x2, and it always comes out to equal the expected value of the xi, that mu. And we've also done the variance of x bar. So the 1 over n came out as a 1 over n squared. By independence, we could split the variances into individual bits, and one of the n's gets canceled. So we've done that computation a lot as well. So that variance and that expected value should not have been a surprise. Okay. Now, one issue is that in practice, when we're given a random sampling of data, we oftentimes don't know what distribution that x1 up through xn came from. So we don't actually know the mean or the variance of the random variables. In which case, we're going to approximate them via resampling and use those approximations in our central limit theorem. So we can approximate the expected value of x bar through permutation testing or later on bootstrapping. We can approximate it. We can approximate sigma squared over n with the standard error of x bar that we can do via some permutation testing or bootstrapping. And then we can use these approximations of mu and sigma squared over n and in the central limit theorem. So now instead of x bar minus mu divided by sigma over root n, we're going to have x bar minus the expected value of x bar over the standard error of x bar. And that will be approximately standard normal. Okay. So if we don't have mu and sigma squared, we'll approximate mu and sigma squared over, or sigma over root n. Okay. So this should actually be a bit of an error on my part. That's replacing sigma over root n, not sigma squared over n, but it's square root. We use the square root to do our standardizing process, right? We don't use the variance, we divide by the standard deviation. All right, so what do we mean by large N? Well, that answer is kind of changing. Before modern computing, we just said, hey, make sure your N is at least 30, okay? Not a great rule of thumb for some distributions, so for some places where the data might come from. In the specific case where the x of i's are coming from a binomial distribution, which we'll tackle in the next video, then a good rule of thumb is we'd like the n times the p to exceed greater than or equal to 10, and n times 1 minus p to be greater than or equal to 10. If those two conditions hold, CLT, central limit theorem's a good approximation. These rules of thumb are less important now, as we'll often use simulation instead of CLT in approximations. So we might use permutation testing, bootstrapping, something else. I'll show you an example when we do the next exercise. Okay, so last panel for this video, got an example here. So please copy. This is example 4.7 from the text. We begin with a random sample of 30 random variables, all from the gamma distribution with r equals 5 and gamma lambda equals 2. And our goal is to approximate the probability that x bar is greater than 3. So perhaps we observed an x bar of 3, and we wanted to calculate a one-sided p-value. So what's the probability the sample mean could be greater than 3? And we can approximate it with the central limit theorem. All right, not important for this problem, but just good thing to remember is gamma variables are the sum of Poisson variables. And if r is 5, then gamma is the sum of 5 independent Poisson variables, all with lambda equals 2, okay? All right, well, otherwise, we know the expected value and the standard deviation of a gamma distribution. So the expected value is r over lambda, which in our case would give us 2.5. The variance is r over lambda squared, so the standard deviation would be the square root of r over lambda squared, which is approximately 1.118. And so if I'd like to calculate the probability that x bar is greater than 3, what I'm going to do is I'm going to standardize it and then say, hey, my standardized thing is actually approximately normal, approximately standard normal, in fact. Okay. So first step is I'm going to subtract my mean and divide by my standard deviation on both sides. And then the central limit theorem tells me that this variable, this new random variable, is approximately standard normal, n01. So I'm going to replace it with z. Simplify that right-hand side to be about 2.4495. Probability z is greater than that would be 1 minus probability z is less than that, which we denote by that, was that capital sigma? Don't quote me on that. But anyway, we get it from our table, or we can have r calculate that for us as 0.99286. And we get 0.00714. So it seems very unlikely that x bar would exceed 3 by chance, okay? Now, that is an approximation, okay? It's not the exact answer. Okay, well, we oftentimes avoid using CLT because we can use R. So I'll now do the same problem on R, but it's also an approximation, okay? All right, so this is also in your, as always, in your notebook, your R file for this, for chapter 4. Okay, so line 79 here, we've got example 4.7. What we're going to do, the gist of it is, I'm going to set the seed that's just going to start randomly somewhere. I'm going to define capital N to be 10 to the 5th, so this means I'm going to be sampling 10 to the 5th times. I'm going to create a vector with that many entries in it, call it x bar, and then I'm going to run a simulation or a loop. So line 86 through 90, here's what I'm doing. For each I between 1 and n, I'm going to do this process. First, I'm going to grab x. X is randomly grabbed from a gamma distribution, 30 values. So I'm going to grab 30 values from a gamma distribution at random. Gamma distribution has what that r equals 5 and lambda equals 2. So I'm going to grab 30 random values, and I'm going to record the mean of those 30 random values in my x bar vector, okay? And then I'm going to show you the sampling distribution, and we can calculate the mean of that sampling distribution and the standard error of that sampling distribution. Well, R will, okay? Okay, so let's run through, let me actually run through this. I set the seed, not important. You just throw in a random number in there and it just sort of randomizes where it starts to randomly split from the gamma distribution. There's my capital N defined, there's my X bar defined, there's my loop. And still running. Oh, again, it's just taking a bit longer. Oh, there it is. And then here's my histogram about to appear on the bottom right. There it is. I'm just going to show you that X bar really does look normal. So there's my QQ norm distribution plot. He says confidently. Don't know where it is. Is it still thinking? I don't know why that's taking so long. I don't know where it is. It is. Well, all right. So much for showing you that. But anyway, let's get the mean of X bar. Something appears to be wrong here. I'm not getting the outputs that I should be. So let me do this. I'm going to try and stop. Okay. Oh, I don't know. Okay, it was just way behind for some reason. There's my normal QQ plot, and it looks pretty darn linear, except for the very right end and left end, right? My mean is 2.4999, which is about what I got with the computation, exact computations. And now I'm looking for my standard deviation. And I get 0.2031483. And we had 1.11. Oh, this is standard deviation outside. I didn't calculate. If you calculate 1.118 divided by root 30, you should get about 0.2. And then I'm looking for the number of times that X bar exceeded 3, and then I'll divide it by capital N, 10 to the 50th probability. I get 0.00927, and we got 0.00714. So we've got approximately the same value. What's the mean of X bar? What does this one do? Oh, just another way of calculating that. Okay, so that's how we'd use R to approximate the probability that X bar is greater than 3, not using the central limit theorem at all. All right, it's the end of this video.